In this video, we're going to have the alkene add to a reagent that could be fitting into this picture that we've thought of before, where there's an electrophilic side and a nucleophilic side of the reagent. That's not obvious at the moment, but again, I have always encouraged you to draw out the Lewis structure for any particular reagent that you're going to use in a mechanism. And what you see here is that you have two bromines, but there can be a distribution of charge within the two bromines such that one end happens to be slightly electrophilic and the other end happens to be slightly nucleophilic, both at the same time. And that's just because these are large and polarizable atoms, so the electron density can be sort of spread throughout. But what you'll see in this particular instance is that the electrophilic part of this reagent, of the bromine, still has lone pairs on it. So though it is electrophilic, it also has a lone pair which can serve to stabilize an intermediate that happens along later in the mechanism. By the same token, in this particular example down here, we have mercury acetate, and this does not fit into our usual paradigm where we have a single reagent that is both electrophilic and nucleophilic. Instead, the way to think about this is that you have an electrophilic reagent, and also there happen to be a couple of other ligands, which are these acetates, which won't participate in the reaction, and then you also have a separate nucleophile, in this case, the solvent, the water. But the reason why I'm putting this on the board at the same time, at least at the outset, is because this reagent has a pair of electrons on it. So again, the question is, what if the electrophilic thing that gets attacked by the double bond itself has a pair of electrons on it? Okay, so let's begin with the mechanism. The double bond goes ahead and adds to the electrophilic side, which causes the electrons to be kicked out onto the other bromine, making a bromide. The equilibrium step will now form the following bromonium ion. It actually forms two different bromonium ions, where the bromine is either coming toward you because the bromine attacked from this outside face, or the bromine is going back away because it attacked from behind the board. Either way, the double bond makes a bond to the bromine, but you'll notice that these bromonium ions have two bonds going from the bromine to both carbons, and that's because the bromine here has lone pairs on it. So as this pair of electrons comes in and kicks out that side, this must also be coming back in to make a bond at the same time. So simultaneous with the double bond attacking the bromine and kicking out the other bromide, the original bromine, the electrophilic bromine, uses its lone pair to stabilize the carbons. And the reason why that happens, of course, is because it will be lower in energy to have the bromine making at least a partial bond with both carbons than it is to have an empty octet altogether. There's a different way to think about this that may be a useful one, and that is to imagine us looking at the cyclohexane ring sort of edge on. So we're looking directly at the double bonds. We sort of picked up this molecule and rotated it, and we're looking head on to the double bond. And what we have floating above here is, of course, the bromine coming in with the other bromine on the far side. So, of course, this is our dibromo species. We've got pairs of electrons everywhere, and what happens is that this relatively polarized Br2 species comes near enough to this double bond to be attacked. And so the pair of electrons comes from the double bond and starts to break the bromine-bromine bond, which is a relatively weak one. Fragmenting those two, this bromine has extra electron density on it, so it goes ahead and adds simultaneously. If you're trying to draw out the mechanism, you really want to draw out both arrows attacking the bromine, bromine attacking back, as well as the other bromine leaving. All three arrows are necessary. So in addition to both bromonium species, where the bromine is making at least a partial bond to both carbons, we also have an honest-to-goodness bromide, which is floating around. The bromide can then add, and there's not going to be any preference whatsoever as to which side of the bromonium it attacks, which carbon of the bromonium it attacks, nor is there going to be any preference over which bromonium gets attacked. All four possibilities are alive. It doesn't matter which carbon gets attacked, it doesn't matter whether it attacks either species, all of those are going to happen. For simplicity, I've removed all but one of the arrows, and we will simply imagine what happens if the bromine comes and attacks this carbon. Well, the answer is it has to come from the backside. This will be an SN2-like process, and the bromide serves as its own leaving group there. And so the end result is that this bromine will end up back, and this bromine will end up. Said another way, the product I expect in the final analysis is one bromine up and toward us, and the other bromine back away, like so. Attack of the bromine, SN2-like process, kicking out that bromide, leads there. Naturally, if this bromine were to attack at this position, again in an SN2-like fashion, if you follow the blue arrows, that also leads to the product drawn. There's no preference whatsoever which side of the double bond the Br2 came in, whether it came in from the top or from the bottom. So there's no preference whatsoever between which of these two bromonium ions you form in the first place. You're going to get a 50-50 mix. And then, of course, there's no preference for the bromine attacking on either side of either of these two bromoniums. So you're also going to get a 50-50 mix. Your products will be the product I indicated originally, as well as its enantiomer, which is to say both bromides, but in the opposite form. The bromine on top now will be coming toward us, and the bromine on the bottom will be going away. So you're going to get a racemic mixture. However, this reaction is incredibly selective when it comes to one specific part, and that is that the second attack, the attack of the bromide on the bromonium species, must occur from the back. It must be an SN2-like process, which means that the two bromides are always going to be anti to each other. They must always come from opposite sides. I'm going to go into the details of this mechanism in a later video, but for now, let me simply say that because this mercury has a pair of electrons on it, much like this bromine does, you will go through a similar sort of intermediate. The water is the thing that actually serves as a nucleophile. The mercury gets attacked by the double bond, and the pair of electrons attacks back. So mechanistically, I will draw this in shorthand form. This comes in, leaving the ligand leaves at the same time as this pair of electrons attacks back. That will then lead to an intermediate which gets attacked by the water. The end result from the first step is that you have a mercury on one side with some ligand bound, and you end up with OH on the other side. Again, this must be an anti-like process. You also make the other enantiomer, so this is going to be racemic. But then, this is not a useful thing for us to isolate and use. So, though this is the first step of the reaction, you have a carbon-mercury bond, and we tend to reduce that in a second subsequent step. So what happens is you isolate this material, then you throw in sodium borohydride. A magical reaction happens. There's a mechanism involved, and I will show that to you, but as far as I'm concerned, this mechanism can remain a black box for you. You don't need to know it. But the result is that the mercury gets replaced by a hydrogen, and this essentially means that you now make a single product. This is a racemic mix when you have the mercury bound, but as soon as the mercury becomes replaced by a hydrogen, then of course what you now have is an achiral molecule. There was a hydrogen at this position as well, and the mercury came forward. Now you have two hydrogens, is that we make a single isomer of this product because this material will be achiral. In answer to the question, what if the electrophile has a lone pair on it, what happens is that your mechanism doesn't go through a formal carbocation intermediate. Instead, what you have are these sort of three-membered species where you have a bromonium, a bromine that has a bond to both carbons simultaneously. Or, though I haven't drawn it yet, that also is what's happening when mercury is involved.